Hi guys, and welcome back to my channel for a final exam review for Organic Chemistry 1. So I have prepared this study guide for you guys, and it's from all of the chapters that are supposed to be in Organic Chemistry 1. And before I start this video and go through these questions one by one, I just want to tell you that you can pause the video before I explain each question and do it yourself, and then watch the video and compare your answer to mine and see what you did, and if you did it correctly, then you can just move on to the next question. So here for the first question, we have rank in order of acidity, and the first one would be the most acidic. So here I'm going to rank them first and then explain why it's in that order. So this is the first one, then we have here second one, and then a lot of people think that this one is the third one when this one is in fact the third one, and then this is the least acidic out of all. And the reasoning for that is because here, once we take the H of A, we have a negatively charged oxygen, right? And then this NO2 looks something like this, a single bonded oxygen and a double bonded oxygen. So this oxygen is negatively charged, which makes this nitrogen to be positively charged. And that is electron, oh sorry, I misspelled electron. Electron withdrawing due to resonance. So I'm going to write the whole reason. Electron withdrawing due to resonance. And that's what makes this molecule extremely acidic, because the conjugate base of this molecule is stabilized by resonance, and resonance is one of the most important effects that we can have on acidity and basicity. So then the second, we have this chlorine substituent, and it's because chlorine is electron withdrawing due to inductive effect. So I'm just going to write inductive effect, but that means that it's electron withdrawing. And for this one, you might think that the oxygen makes it, for this molecule, you might think that the oxygen makes it electron withdrawing, similar to the second one here, because it has an inductive effect, an electronegative atom attached to the ring. But this one is a strong electron donor. This is important, so I'm going to write the whole thing down. It's a strong electron donor, and that's due to resonance. And if you want to see it, you can draw all the resonance structures of this molecule, which has only an OCH3 attached to it, to see that it puts that OCH3 group puts a negative charge on the ring. And that's not what we want, because we already have the negatively charged oxygen. So that makes it a really bad acid compared to the rest of the molecules that we have in this question. So moving on to the next question, we have ranking carbocation stability. And as we can see here, the first one, A, is an allylic carbocation. B is just a regular primary carbocation, which is the least stable out of all these. And so I'm just going to say this is the least stable. And then we don't need to bother ranking the rest of them, but I'm just going to say that C is allylic. So comparing A and C, A is definitely more stable because it has so many resonance structures because of the triple bond that we have in the aromatic ring. And then D is just a secondary carbocation. So yeah. Moving on to the next question, we have mark the relationships of the following molecules as either same, enantiomers, or diastereomers. So what I would do for part A, I would just draw this molecule, the second one, in the chair conformation. And so here for this OH group, I'm just going to put it up similar to the OH group here because I want to compare. And then looking at the second OH group here, I see that they are trans to each other. So if I have the OH group on this carbon up, then I'm going to have it down here, which is exactly the same as what we have in the molecule to the left. So these two are the same. Then for the next one, this one is kind of my favorite because the easiest way to do this and make sure that you get to the answer in the fastest possible way is to assign RNS to these two stereogenic centers. So here, this carbon has the assignment of R, and then around this carbon, it's S. You can go ahead and try to figure that on your own, but these are R and S. And similarly here, what I do for Newman projections is that I see this H, which needs to be on the back. So I try to look at this carbon from this side. So I'll put my eye here. And then I see that the CH3 is on this side, Cl on this side, which is the first priority. You have the second priority to the back. So if you just look at it from that angle, you'll see that it's R. And then do the same thing for the carbon in the back, except that H is on that side. So now you need to be looking at it from this angle. So put your eye here, and you'll see that the assignment for that one should be S. So these two are exactly the same, so the relationship between them is same. They're the same molecule. One of them is the Newman projection, the other one is just a regular molecule. Next question we have, is the molecule below chiral or achiral? So first of all, we have sp2 hybridized carbons all over this molecule, but another reason for this molecule being achiral is that we have a plane of symmetry here. So kind of if we lay that molecule on a desk, on a surface, on a flat surface, we see that that surface is literally the plane of symmetry for that molecule. So it's achiral. All right. And then here in the next question, we have what are the reagents necessary in each case? For the first one, we see that this alcohol, this primary alcohol, is getting oxidized to a carboxylic acid. So what we need is a strong oxidizer. In this case, I'm going to use K2Cr2O7, but you can use anything else in acid, H2SO4. You can use K2CrO4 or NaCr2O7 or anything of that sort, which is a strong oxidizer. And then here for the second one, again, we have a primary alcohol, but it results into an aldehyde. So what can we use to stop this reaction, the oxidizing reaction, at an aldehyde? We don't want to go further to a carboxylic acid. We don't want this to happen. We're going to use a mild oxidizer, which is PCC in this case. And usually in organic chemistry 1, the only thing that we use as a mild oxidizer is PCC. And then for this next one, for part C, I'm pretty sure there are multiple ways to go about this one, but the way that I want to go about is to use Br2 in light, HNu, and you get this Br substituted cyclopentane, and Br attaches to the most substituted carbon, which happens to be this carbon, and then you can use a strong base such as NaOET, which ET stands for ethyl, and this would be an E2 reaction. So that's how it would go about that one. You can also use hydroboration and then hydration, but that's totally up to you. And then moving on to the next question, we have name the following molecules shown below based on the IUPAC rules. So here the functional group is this OH group, which is kind of important. So 1, and then if we go that way, the second group comes at carbon 3, versus if we go this way, we have the second group on carbon 2. So we're going to choose this way, and I'm going to erase this part. So we have 1, 2, 3, 4, and 5. And then next thing you need to do is to assign RNS to these groups. Here we have R, here we have S, and then R again here. You can go ahead and practice it to make sure that those are the right assignments. And then the name of this molecule would be 1R, 2S, 5R. We put all of those assignments in parentheses, and then dash 2 isopropyl. So the I in isopropyl gets priority over the methyl because that starts with M. And then 5-methyl, then the whole thing is just a cyclohexanol. There we go. I can move this to the left. So all of it is in the box. And yeah, for the second one, we have this double bond in the ring, which is really important. The most common mistake that I see students make is starting from this side of the double bond and go like 1, 2, 3. But don't forget that you need to cover the double bond. That's really important. So make sure that you are covering this double bond right here when you're assigning numbers. So it should go like 1, 2, 3, and 4. So what you have right here is 4-methyl and then just cyclohexene because it's an alkene. And then for the next molecule, they write it this way. They put the branch with most carbons kind of like as a branch, not as like the parent chain, so that they can trick you. But as you can see, this is the longest chain that we can see in this molecule. And then I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. So we have an octane. And then we have 2 substituents on the 4th carbon of the parent chain. So we have 4-ethyl, 4-methyl, octane. And yeah, that's pretty much it. And then for the next question, we have predict the product of the following reactions and assign a stereochemistry whenever it's needed. So for the first one, we know that hydroboration happens in a syn fashion. So it's a syn addition, we already know that. One other thing that we know is that the OH adds to the less substituted side of the double bond, which happens to be this carbon. And to draw the product, you're going to have this 5-membered ring, and then we have the CH3 coming out of the page, and then notice how the OH needs to be going into the board because the keyword here is syn addition. It means that the H and the OH group add in a syn fashion to this double bond, and as you can see, the H here is to the back, so both of them are on the same side, which means they added in a syn fashion. And don't forget to add plus an antiomer. You can either draw it or just add the word enantiomer. Then for the next one, we have this chair conformation of a cyclohexane, and then you're adding acid to it, HgSO4 and H2SO4. So you're going to get an enol first. You can go ahead and draw it out. I'm not going to do that. And then that's like the transition state, and then you get a ketone. Here we go. Ketone. And the conformation doesn't change because this carbon is not involved in the reaction at all. Moving on to the next question, here we have how many monochloro derivatives of 2 and 2 and 4 trimethylpentane are there? In other words, how many products of chlorination would you get starting with 2 and 2 and 4 trimethylpentane? So I'm going to draw this molecule out. This is what 2, 2, 4 trimethylpentane would look like. And basically they're asking how many products of chlorination you would get. So the thing about chlorination using H-nu or light is that it gets priority, no carbon gets priority over the other carbons, unlike bromination. So you can have the double bond you can add the chlorine anywhere to this molecule. So here you can add it there. I use this arrow technique. And then here you can't put a chlorine because you already have 4 carbons around that carbon. You have 4 bonds. So the next one would be here, and then you can put here, and then one here. And then notice how you can't have any chlorines on these carbons because they're identical to these two. So you can have a total of 4 products. And since they didn't mention anything about a stereochemistry, I'm just going to assume that you'll get 4 products. But if you want to have a stereochemistry involved as well, you have to consider the different possibilities that you might get. So these would give you only 1 product each because there are no 4 different groups around the carbon, except for this middle one that you'll get 2 enantiomers if you want to consider stereochemistry. So you'll get 5 products. But in general, the answer should be 4 products. Alright, and then moving on to the next question, we have which form of that molecule is more stable, gauge or anti? And explain. Oh, that was actually right. It was off. Okay, so I know a lot of you just want to go ahead and say it's the anti form, but be careful about these questions. There is a reason that they give you this question on an exam or on a homework. It's not just you can say it's anti and move on. You need to draw the 2 different structures. So the first one that I'm going to draw is the anti form of that molecule in a Newman projection, because that gives us better insight to why anti or gauge should be better than one another. So here you have OH and then H, OH, H. This is the gauge form. So notice something going on in the gauge form. Yes, it is the intramolecular hydrogen bonding that's happening in the gauge form. Because here you have this hydrogen bonded to oxygen, which forms a hydrogen bonding right there. So that makes the gauge form more stable. So see how in this case, anti is not the more stable one. And this is personally my favorite question because it's kind of a trick question. You have to consider everything that is going on in the molecule to get to the right answer. And then finally, the last question, we have draw the energy diagram for the reaction below, write a rate equation for it. What would happen if the concentration of methoxy ion was doubled? So you don't really need to know what exactly is going on in this reaction. The key is to look at the 2 different steps and see that the first one is slow. So that means that that equation, that reaction, is the rate determining reaction. So in order to write the rate equation for the whole reaction, we have R is equal to K, and then the reactants of the first part, which happen to be these two. And then in order to draw the energy diagram for this reaction, you need to draw, so we have energy and then reaction here. So it will look something like this, because the first part is slow, the second part is fast, and that's the activation energy that you see, the difference of activation energy you see here and here, that makes them slow or fast in comparison. And the general like delta H decreasing form is because the Cl and this molecule that we have right here, they have more, they're going to have more movement than the starting material, so that's why you get this form of the energy diagram. And then lastly, we have what happens if the concentration of methoxy ion is doubled. So if this is doubled, then the rate of the equation is going to be doubled as well. And here we go. And that was pretty much it for the study guide that I had prepared for you guys for Organic Chemistry 1 to kind of go over and get prepared for your final exam. I hope you all do good on your exams and in your semester overall. Thank you for watching this video. Make sure you give it a thumbs up. Bye.